things to do here today. We're going to finish one and start one. So we're going to kind of wrap up, sort of wrap up our discussion of derivatives, of how we calculate derivatives, right? So we're going to work in reverse a little bit. I would like you to tell me here, I'm giving you a limit, and I want you to tell me that limit represents the derivative of what function? And don't say it out loud, just everybody think about this a little bit. That limit that limit represents the derivative of what function? What function am I starting with and trying to differentiate? Remember, that's our verb for derivative. If you take a derivative, that process is called differentiation. Okay, it might be helpful to remind ourselves what is the definition, the limit definition of a derivative. You tell me. Limit of x as okay. So what's the function? There's a pretty easy place to spot it. Sine 2x, yeah, absolutely, right? How come? Right there. Okay, so that is, working backwards, we were just trying to take the derivative of the function sine 2x, right? Okay. Well, that wasn't challenging enough. So let's try this. Okay. So this time I want to know two things. I want you to determine what the function is you're trying to differentiate, and I want to know at what point are you trying to calculate specifically the value of the derivative. So again, two things. I want to know, part one, and question two is, what's the point of tangency? In fact, yeah, let's find the whole point of tangency. Okay. You're right. You're right. So we know f of x is the square root of x. Okay. And what's the value of x, call it a, at which we're trying to evaluate this derivative? It's at 7, isn't it? Right? How come? Well, here's why. Because look, we're trying to plug in a value of ax equals a equals 7 because of that, right? Everybody see that? So really, what have we done here? We've just said that we've done two things. We said that f prime of x equals the limit of square root of x plus h minus square root of x over h as h approaches 0. And then we said f prime of 7 would equal square root of 7 plus h minus square root of 7 over h, the limit of that. Whoops. As h goes to 0. Everybody see that? Okay. Okay, just kind of pattern recognition. So then what would our point be? The x coordinate is 7. What would the y coordinate be of our function? Square root of 7, right? Because if we know so we get the ordered pair, 7 square root of 7 is our point of tangency. Okay? A little bit, wasn't it? Yeah, kind of having to work backwards. Okay, so I want to show you, this is kind of optional. You don't always see this, but I want to show this to you, just so you can see what the logic behind this is. There is an alternate form of the difference quotient, because remember, all the difference quotient is just the quotient that defines the slope of a secant line, right? So previously, we looked at this as the point x f of x, and then the point x plus delta h, f of x plus delta h. We called it delta x at the time, but we'll call it h now, right? X plus h and f of x plus h, okay? And then we moved these points together by taking a limit to merge the 2 points that defined the secant line into a single point, which turned it into a tangent line, right? Now we can do the same thing by defining those points differently. We could call this, for example, this point is a f of a, and this point is x f of x, and we're just going to take a limit as x approaches a, and it would accomplish the same thing, wouldn't it? Wouldn't it just migrate this point backwards then as x gets closer and closer to a until it merged with this point in the limit and we created a tangent line, right? So we could just write the slope of a secant line as f of x minus f of a over x minus a, and the slope of the tangent line would just become the limit of that as x approaches a. Okay, and we can do algebra on that the very same way we did algebra previously on all those examples we've looked at with calculating derivatives using limits. Let's take an example. I thought we were going to take an example. Where is my example? I meant to have an example. Okay, I'm going to make an example. So what if we did, man, I had a really good example too. Where'd it go? I don't think so. It's supposed to have been, well, I mean, okay, so here's a quick, I'll make one up. Here's a quick example of how, comparing and contrasting those two types of limit definitions. Here's the one we started with. The normal one that we use most of the time is the h definition, right? As h goes to 0, we take a limit as, whoops. Yeah, this got really messed up. You know what? I know where it is. I know where it is because I renamed it. Give me a quick second here. So this is, let's try it on here. I think it's right here. Well, that didn't do it, did it? I can't remember where the heck I put that thing. Well, I'm not going to worry about it too much. Get in there. Driving me nuts. Yeah, you bet. Okay, well, anyway. So, you know, we had, this should have been an H, right? Not a... And, you know, this would have been the general form of the derivative. This would have been a specific value if I'm plugging in 5 for x, right? I'm actually trying to calculate f prime of 5. And here it would have been if I'm using the alternate form of the difference quotient. Now, I want you to notice something. When you write out the alternate form of the difference quotient, notice that the way you write it is f prime of a, because we're going to take a limit as x approaches a. So we would end up getting some answer like f prime of a equals 2a or something, which would mean that f prime of x would just be 2x. Okay, so let's do an example. I'm going to make one up. How about if we want to take the function, we want to use the alternate form of the difference quotient with the function, how about f of x equals x cubed plus 1. That would be a good one. Okay? So we got to start off with the template, and then we'll fill in specifics. So if we're going to use the alternate form, what was that? F prime of x, actually f prime of a equals what? Limit good over as, okay, there it is, right? So we're just going to plug this in. So then if I use our function, specific function f of x, what does that become? Yeah, right? Because what's f of x? It's x cubed plus 1 minus, let's make that minus, and let's make this green, minus f of a. Well, what's f of a? If f of x is x cubed plus 1, what's f of a? Yeah, but what is it? If f of x is x cubed plus 1, what's f of a? A cubed plus 1, right? We're just inputting an a instead of an x. No, they're not. They're different. They're never equal. X approaches a, but it never gets there, right? Okay, all divided by.
Why did you use a cube? Why did you just get to put the a in there?
Say it again.
Why did you just get to put the a in there and call that the equation for f of a?
Yeah.
Why?
Why can't I? Well, because what do you do when you evaluate something? You're substituting a value for x. So how would you calculate f of 2? Yeah, it'd be 2 cubed plus 1. How would you calculate f of bus? It'd be bus cubed plus 1. What's f of a? a cubed plus 1. It's just this is the rule or the pattern you follow when you input a value, right? I'm just inputting a this time instead of x, okay? So we're taking this limit as x approaches a. Now what's going to happen if I try to evaluate that directly?
One will cancel.
And, well, if I let x go to a, if I replace the x's with a's, don't I just get 0 over 0? Okay, you knew that was happening, right? Right, I mean, you see what I'm saying? Then you're going to get like, I'm going to get a cubed plus 1 minus a cubed minus 1. Well, that all adds to 0 over a minus a is 0. So it's indeterminate. So we've got to do some more work. But what do you think the more work is going to look like here? I mean, yeah, you're right. But you can already predict what are the factors that are going to have to cancel. If x is approaching a, if that is producing an indeterminate form of a limit, you already know what the factors are that are going to cancel. Well, x minus a, right? X is approaching a. What if x were approaching 2? Then the factors would be x minus 2, because the x value that, when x equals 2, what's the factor that goes with that? X minus 2, right? When x becomes a, what's the factor that has that 0? X minus a. So you already know that's what has to happen. The x minus a's have to cancel. Well, and you have an x minus a in the bottom, so it's got to cancel, right? We just have to make that happen. So go. Make that happen. What do you do? Okay, so we distribute the negative 1. Okay, so then this is going to become the limit of, if I distribute this, everybody agree the 1s are just going to cancel?
Yeah.
I'm going to get 1 minus, so I'm going to get the limit of x cubed minus a cubed over x minus a as x approaches a. Now what? We're not going to expand it. We're not going to expand it. What are we going to do? Factor it. We're going to break it into a product of factors. That's the difference of cubes pattern, right? Yeah, so how's that work?
Start x minus a. It has to start x minus a. Let's start with x minus a.
Yeah.
So, plus something. 3a.
No, it's just AB. So XA in this case, plus B squared. Remember how that works. You're going to get a linear factor and a quadratic factor. The linear factor is always going to match, it's going to be the same sign, right? The quadratic factor is going to be all the different ways of multiplying those things and those things. X times x is x squared, x times a is x times a times a. Oops, that's supposed to be, I get it. That's supposed to be a, you know what I was thinking in my brain. I got confused myself. I was thinking of the pattern with a's and b's. Right. So that's an a. And then a times a is just a squared. And remember what our rules were. We said the signs are going to be same, opposite, plus every time. Remember talking about this a couple years ago? Okay, divided by x minus a as x approaches a. And look at that. Okay, that's pretty good. And now I can take my limit as x goes to a. I can evaluate directly. So what do I get if I evaluate that directly? That's just equal to, well, the limit of x squared plus xa plus a squared as x approaches a. Isn't that just a squared plus a squared plus a squared? 3a squared. How about that? So f prime of a equals 3a squared, then f prime of x would equal what? We did it. Okay? We just did a derivative using the alternate form of the difference quotient. I can't find any of those in any textbooks, so I'm trying to put one on this an assignment, so I'm probably gonna have to build a couple. So you gotta give me just like a little bit over lunch today to get those built, and then I'll put that assignment
Is
up.
it always going to be like the same thing, just with the variable?
Yes,
Okay.
yeah, yeah. That, you mean A turns into X, you mean? Yeah, it does. And how come? You can see why that is. Because in this case, we're taking a limit as X, which is the variable, is approaching some value A, right? You could say as A approaches X, but that doesn't really make any sense because typically you're trying to find the derivative at a specific point. And so we always let X approach A, okay? But really all you're doing is you're just establishing a pattern. You know, here's the pattern. The derivative of something is 3 times that something squared, right? Okay. Derivative of f of something is 3 times that something squared. Okay. So I think, yeah, we're good with that one. Okay, what I want to start talking about today